Okay. So here's what we came up with yesterday. We came up with, so far, 3 equations. We have P equals V naught plus AT, distance equals 1/2 E plus V naught times time. The distance equals 1/2 AT squared plus V naught time. Okay? Now, all of them are unique based upon what you have in terms of the information that you have and you're given. So, what the unique thing you'll see about this first equation is that that's the only one that doesn't involve distance. We're going to have 4, we're going to actually end up with 4 equations today. This is the only one that doesn't involve distance. All the other ones do. This is unique because this is the only one that doesn't involve an acceleration. Okay, all the other ones will have an A. This is unique because this is the only one that's not going to involve final velocity. Okay, so they all kind of have their niche thing. And trust me on this one. Here's the worst thing that you can do. The worst thing that you can do when you read these problems is to sit there and go, ooh, what equation am I going to use? Okay. It's going to be a train wreck. I'm telling you. The best thing you can do is figure out what information that you have, figure out what you're given, figure out what you're trying to find, and then go from there. So let's work like a simple example. Kind of show you how this deal plays out. So let's say that we're going to have the famous carrot car, and we'll make it simple and we'll start it from rest. Okay, initial velocity is going to be 0. And we're going to have it accelerate at 4 meters per second squared. And we're going to look at what's going to happen at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds. So imagine this. You're in the carrot car. We're at rest. We're going to press down on the gas pedal. 4 meters per second squared is a fairly decent acceleration, okay? It isn't like throw your back in, in the seat kind of thing, okay? But it's a fairly decent acceleration. And so there's a whole bunch of things that I want to do with this. So I want to figure out what the velocity is at each second, like how fast is it going after 1 second, 2 seconds, 3 seconds, 4 seconds. I want to figure out how far it's gone at the end of 1 second, 2 seconds, 3 seconds, 4 seconds. I want to draw a position time graph, and I want to draw a velocity time graph. Okay, so I want to do all of that knowing an acceleration and the values of time. Okay, figure that all this out. So let's start with the idea of just what acceleration is. Okay, so remember, acceleration is not how fast you go. It's the rate at which your velocity changes. Okay? So if you look at an option, if you go with the VDAT chart, okay? And you don't have to do this, but if you get into a problem and you read it and you go, man, I have no idea what's going on, okay? At least figure out what the variables are. You only have 5. Okay, there's 5 variables, 4 equations. Okay, that's all you can have. That's it. We don't have to worry about mass. You don't have to worry about force. You don't have to worry about energy. Any of this at this point. You just have to worry about these variables. That's it. So in this situation, we're going to start at rest. Okay, that's going to be 0. Eventually, I'm going to look at what's going to happen to my distance. I'm going to look at what's going to happen to I know my acceleration, which is 4 meters per second squared. I know my values of time, 1, 2, 3, and 4. Final velocity, I don't know. But I know an acceleration. I know that I'm going to be speeding up. Got a whole bunch of things that I do know, but yet a whole bunch of things that I don't know. So, let's actually start in a weird way, but let's start with the velocity time graph. Okay? So clearly my velocity time graph is going to start at 0. Okay? Now, I know my acceleration is going to be 4 meters per second squared. So Peyton, how does that acceleration of 4 meters per second squared, how is that going to be a factor on my velocity time graph?
It's going to be the slope.
Perfect answer. It's going to be the slope. Okay, so let's talk about what that slope means. So the slope of this line is going to be 4 meters per second squared. Okay? So we're going to look at 1, 2, 3, and 4 seconds. Okay? That's what we got going. So since that slope is 4 meters per second squared, we're going to start at 0. So if you look at this in terms of a y-intercept, okay? Oh, this is a linear function. I don't have the same acceleration. It's a linear function. My y-intercept is going to be 0. Oh, cool. Because the velocity starts at 0. If the car was already moving, it wouldn't. But the car is going to start at rest. Okay. So here's the million-dollar question. Jack, I'm going to start at 0. The slope of this line is 4 meters per second squared. So at the end of 1 second, what's my velocity going to be?
It's going to be 4 meters a second.
Fantastic. Okay. So at the end of 1 second, I'm going to be traveling 4 meters per second. That's what that acceleration is. Okay. What that says is that for every second that goes by, my velocity is going to increase 4 meters per second. That's what it means. Okay. At the end of 2 seconds, I'm going to gain another 4 meters per second. I'm going to be up to 8. I'm going to be up to 12. I'm going to be up to 16. That's what that slope means. That's why I said your acceleration tells you the rate at which your velocity changes. It doesn't tell you how fast you go. So what this means is if I come up here to 4 seconds, I'm going to be going 16 meters per second. So I can draw this nice linear function with a slope of 4 meters per second squared. So if you're a graph person, okay, and I'm going to show you different ways that you can view this problem. And the more diverse ways that you can look at a problem, the better your chances are going to be of successfully solving the problem. Okay, hey, I got a slope. Oh, that's my acceleration. Oh, right, every second that goes by, I'm going to go from 4 to 8 to 12 to 16. Okay, that's one way you can view this. So that's one option. So if you were to set up a chart and go, okay, here's my velocity, here's the distance traveled, and here's my time. So if you're a chart kind of person, okay, I was president of the chart club in high school. Okay, good for you. So at the end of 1 second, I was going 4 meters per second, then I was going 8 meters per second, 12 and 16, okay, because that's what that slope means. Oh, this is the rate at which my velocity changes. Okay, cool, all right? Now, let's say you go, but Mr. Burkamp, I'm a formula kind of person. How can we use formulas? Oh, okay, well, you can look at this and go, okay, well, V equals V naught plus AT. It's a linear function which matches with this graph. Oh, that's my y-intercept. My initial velocity is 0. The car started from rest. That's a 0. Oh, okay. I don't have to worry about that. Initial velocity is 0. So I'm going to have my acceleration, which is 4 meters per second squared. And then I'm just going to plug in different values of time. I'm going to plug in 1 second. I'm going to take 4 meters per second squared times 1 second. The seconds cancel out. I get units of velocity. I get 4 meters per second squared. If I want to figure out how fast I'm going at the end of 2 seconds, I'm going to take 4 meters per second squared and multiply that by 2, and I'm going to get 8 meters per second. So if you're a formula kind of person, it's like, Mr. Burkamp, I like punching numbers into formulas. Good for you. Okay, the world needs people like you. You can do it that way. Okay, you can draw the graph, figure out the slope of the line, figure out how fast you're going. You can do a formula. I don't care. Pick the one that makes the most sense to you. Okay, so we got that one done. Now, let's talk about how far we're going to travel. So, could I, because I want to know how far it's gone at the end of 1 second, could I do this? Could I just say, well, I was going 4 meters per second at 1 second. Could I just take 1 second and multiply that by 4 meters per second and go, oh, I went 4 meters? Is that cool? Math is simple. I'm going 4 meters per second, I went 1 second. There you go. Derek, what are your thoughts?
Yes.
Yes. Anybody else think that that's a cool way to figure out how far we've gone? Just take 1 second times 4 meters per second. No! Stop! No! 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 Stop! Gray hairs just sprouted all over my head. You're trying to use distance equals velocity times time. You're trying to take 4 meters per second times 1 second. What did I tell you all yesterday not to do?
Never use it.
What did I tell you never to use in this unit?
Just
That equation. What did you just do? Then yesterday you all said, Mr. Burkham, we won't do that. And I said, you lie? You lie. And here it is. No, stop. Bad. Horrible. Okay? Is it going 4 meters per second the entire time? No, what's the only time it's going 4 meters per second? At exactly 1 second. At a half a second, it was going 2 meters per second. At a tenth of a second, it was going 0.4 meters per second. Okay? It's only going 4 meters per second at that exact time of 1 second. Okay? It's bad. Stop. No. Horrible. Don't. Okay? But. Let's talk about the velocity time graph. Here's my velocity time graph. So I'm going to draw this a little bit big, and I'm going to say, okay, here's 1 second. And there's 4 meters per second. Okay? So this is what this is saying. At the end of 1 second, I'm going 4 meters per second. Now, to redeem yourself, okay, I'm trying to undo some of that gray hair that you just caused me to have. Okay? Could I use this velocity time graph to figure out how far the car went?
Yes.
What would you do?
Find the displacement.
Which would be representative of the, on a velocity time graph, displacement equals
The area.
the area. And this looks surprisingly like a triangle.
Yeah.
I might be wrong, but I think it is, last time I checked. And how do you find the area of the triangle?
1/2 base times.
Oh, 1/2 base times height. Oh, you go, Mr. Burkham. I'm the president of the area club in high school. Good for you, okay? So this is 1/2 base times height, okay? This is valid. I could use my velocity time graph, okay? I could use my velocity time graph to find the area, to find the displacement. So I could sit here and go, oh, that's 1/2 my base, which is 1 second, times my height, which is 4 meters per second. And oddly enough, I get, wait for it, 2 meters per second. Okay? It's cool, right? 2 meters per second. Fantastic. I can use that graph. It's great. I can do that. That's one option. You go, Ms. Burkham, can we talk formulas? We can talk formulas. We know distance equals 1/2 v plus v naught times time. Oh, okay. At the end of 1 second, we were going 4 meters per second times 1 second. It's cool, right? So I get, oddly enough, 0 plus 4 is 4. Half of that is 2. 2 times 1 also gets me 2 meters. Okay? That's another way that I can do that. It's cool. Like, oh, basically what we're saying here is that on average, I'm going 2 meters per second. Because I started at 0, I ended up at 4. 1 second later, so on average, I'm going 2 meters per second. Okay? Notice that this math here is the exact same as that math up there. I'm taking 4, I'm dividing it by 2, I'm multiplying it by 1 second. Okay? Because if you average this out, that looks like a rectangle at 2 meters per second. Okay? I can do that. Now, ironically, I wouldn't recommend that you use either of those methods. Okay? I would not recommend it. And here's the reason why. You are using a value that you found previously of 4 meters per second. Okay? So if you screwed up the calculation at 4 meters per second, then your answers are going to be wrong from there on. So generally what you want to do is that you want to use values that are given to you in the equation as long as you can, okay? Now, you are going to reach situations where you have to use derived value. You don't have a choice, okay? But you want to put that off as long as you can. So what I would recommend that you do to find out how far it went, and you'll see that this is actually more of a hidden truth. Distance equals 1/2 AT squared plus V naught time, okay? If it were me, this is the one that I would use, and here's the reason why. That initial velocity is 0, so when you see me draw like an arrow and then go to 0, that's just like a sign that says this part of the equation drops out, okay? I don't have to worry about that because my initial velocity is going to be 0. I gave you the acceleration and I gave you the values of time. You didn't have to derive those values, okay? So if you don't, you want to use equations where you can work off numbers that you have in the problem as long as you can. Because if you screwed up that final velocity calculation, your distances are now going to be wrong, okay? So we're going to use this a lot because for those of you that have studied functions, this is a function equation. This is going to tell us is how far you have gone as a function of time, okay? So you can plug in any value of time and figure out how far that you went without having to go off of the final velocity. So whenever you start from rest, and a lot of times we're going to do this, like for example, tomorrow we're going to talk about gravity. Oh, I dropped something, okay? It falls from rest. The initial velocity is going to be 0. So our car starts from rest. So anytime something starts from rest, this is a good equation to look at. Now, here's what's going to be more important, is that notice that this has t squared in it, okay? So when any time you see an equation that has something squared, that means that it's going to be a quadratic function, okay? It's not going to be linear. Now, so I want to do a little compare and contrast. If you look at your velocity, v equals v naught plus at. Notice that velocity changes as a linear function of time, because that's just acceleration times time. Displacement changes as a quadratic function of time because it's at squared. So whenever you see something squared, that's a quadratic or exponential relationship. If it's just at, that's a linear function because it's just a slope function. Okay, it's a linear function. So here's what we're going to do. We're coming here and go, okay, 1/2. My acceleration of 4 meters per second squared. I plug in 1 second. I'm going to square that. Oddly enough, I'm going to get 2 meters. Now, if I want to figure out how far I went at 2 seconds, okay? Now, here's the other thing that I want you to see. That is t squared, okay? That is t squared. It's going to be huge, it's t squared. So if I square 2, I get 4. 4 times 4 is 8. And then, 4 times 4 is 16. Half of that I get 8 meters. And then if I go to 3 seconds, I get 18 meters. Okay? Now here's what I want you to look at. Notice when I go from 1 second to 2 seconds, notice that I doubled the time. I doubled the time. I went from 1 second to 2 seconds. But notice that my distance increased by a factor of 4. Okay? So when something is squared and you double it, whatever you're talking about is going to increase by a factor of 4. In this case, I tripled my distance, okay, or time. I went from 1 second to 3 seconds. Notice that my time increased 3 squared, which is 9. I take 9 times 2, I get 18. So whenever you make changes to something that's squared, small changes to that make a big difference because that value is squared. So generally you talk about doubling something. Oh, I doubled the time. Distance is going to go up by a factor of 4. I triple my time. My distance is going to go up by a factor of 9. Okay? So focus on something that's going to be squared. Now, if you go to the 4-second mark, 4 meters per second squared times 4, 16, 832 meters. Okay, now, let's look at this position time graph. There's 1 second, 2, 3, 4, 4, 8, 12, 16, 24. Okay, so at 1 second we were at 2 meters. 2 seconds we were at 8 meters. 3 seconds we were at 18. 4 seconds we were way up here at 32. Now, look at this. Notice that this graph is this nice parabolic curve. Okay? Now, this is a position time graph. This is where a whole bunch of things hopefully make sense. What does the slope of a position time graph give you?
Velocity.
Velocity. Gives you velocity, right? So what's happening to the slope of that line as time goes by? Slope is becoming steeper. Why is the slope becoming steeper? What's happening to the velocity? It's increasing. Oh, the velocity is increasing, the slope is getting steeper. Oh, there you go. Now, here's the kicker. This is where everything falls into place. I'm going to come out here to this 1 second mark, and I'm going to draw a tangent line that touches that line at the 1 second mark. What's going to be the slope of that tangent line at 1 second? Connor.
4 meters per second.
Why?
Because it's just the velocity.
Yeah, that's how fast it's going at 1 second. At 1 second, if I were to draw that tangent line, that would have a slope of 4 meters per second. Oh, that's kind of cool, right? If I go to 2 seconds and draw that tangent line, that slope is going to be 8 meters per second. If I go to 3 seconds, that slope is going to be 12 meters per second. If I go to there, that's going to be 16 meters per second. So notice that my tangent lines are becoming steeper and steeper and steeper because my velocity is increasing, so therefore my slope is getting steeper and steeper and steeper. That's how everything fits together. Now, so here's what I want you to take out of this. Whenever you see, and this is this contrast, you have V equals V naught plus AT, you have distance equals 1/2 AT squared plus V naught time. Because this is squared, that changes as a quadratic function of time because it's t squared. So position changes as a quadratic function of time. Velocity changes as a linear function of time. Okay? I promise you, I'm going to ask you this question on the acceleration test. Okay? I promise you, which is probably going to be that'll be the middle of next week. It's going to be a multiple choice question. I'm going to ask you, how does the velocity change when you have uniform acceleration? Oh, that's a linear change because it's AT. How does position change as a function of time? Oh, that changes as a quadratic because that's t squared. Okay? You don't have to memorize it. Just look at the equations. Oh, that changes with t squared. Oh, that's just acceleration times time. So this is why velocity time graphs, every velocity time graph you're going to draw is going to be some sloping line, positive, negative, something like that. It's going to be a straight sloping line. We're going to assume that your velocity is changing at a uniform rate. Any position time graph that you draw is going to be some curved line, curving up, curving down, something like that, because your velocity is always changing. Okay? There you go. Got it? Good, great. Now, you're going, that's great, Brookhampton, but how do I use this? Okay? How do we actually use these equations? It's a valid question. So here's what we're going to do. So I'm going to try and get a little bit of a runway here so Donna can see what's going to happen. So what we're gonna do is I'll take the fan cart, we've dealt with this before, okay? Or not. Why is my fan cart not working? This is awkward. Da-dee-da-da. Da-da-da. Well, this sucks. Okay, hold on. I have a backup. Backup. Okay, we got plan B.
I'm gonna zoom out so she can
So we can do this. Okay, so did you see this? Yeah. Okay, so what we're gonna do is I'm gonna try and determine the acceleration of that cart. Okay, so I'm gonna put this on the table, and here's gonna be the cart. And here's going to be the fan going to go like this. So what are some things that we could measure? I can measure distance. Oh, how far is the cart going to go? I can measure that distance. That's simple to do. Okay? What else can I measure?
How long it takes.
Huh?
How long it takes.
Yeah, I can measure time. Okay? I can measure distance, I can measure time. Now, velocity is tough to measure, okay? And I'll tell you why velocity is tough to measure. Because by virtue of the fact that we're saying it's accelerating, that means that the velocity is always changing, okay? So to try and get the velocity at any point in time is tough, mainly because it's always changing. But we're clever though. If we're clever, and we are, what do you think we want? What do you think we're going to have the initial velocity of the cart be?
0.
0. Okay, so we're going to let the cart start from rest. So if you go with what Izzy said, okay, we can measure distance, we can measure time, and I want to get the acceleration. Okay, so look at this. If you go with the VDAT chart, V naught, DAT, I can measure some distance. I can measure how far it's going to go. I can get this number. I can measure time. Got a stopwatch. Oh, cool. I can measure time. I get distance, I can get time. My acceleration is what I don't know. And we're clever. So we're going to let the initial velocity be 0. Okay? We could have it moving, but that's going to be tough. Mainly because then we'd have to know what that velocity is. So, final velocity right now isn't part of the story. So here's what we're going to do. So, I'm going to put this over here on the table. Donna, you're just going to have to take her word for us that this is what's going to happen. So, I need you to run that stopwatch. Sorry, Donna. That's personal. Physics teacher coming through. Okay, so we'll go on warp speed, okay? And, we'll go a half a meter. Okay, so I'm going to tell you when. All right, you ready? 3, 2, 1, go. Oh, hold on. Stop that. We're going the wrong way. Okay, let's try that again. 3,
Hold on,
2.
it's not resetting. How long is it to reset?
Hold on. Take a little bit for it, Donna. Reset. Push down a little. Okay. Let's try this again. Okay, you ready? 3, 2, 1, go. Stop. Okay, what do we get?
30.
Fantastic. Okay. So, here's what you're going to do. again, if you look at how I solve every problem, here's the sequence that I do. I figure out what I have, my distance is a half a meter, and my time was 3.50 seconds. And I'm trying to find the acceleration. So the first thing I'm going to do is I'm going to go, okay, here's my equation. Distance equals 1/2 AT squared plus V naught time. That's what I'm going to start with. That's my equation. Okay. Now, I know my initial velocity is 0, so that whole thing goes away. Now, I need to solve this for acceleration. Okay? I need to solve this for acceleration. So, Miss Elliott, what does that equation look like solved for acceleration? What are you going to do?
A equals V over 1/2 T squared.
I hate fractions. Get rid of the fractions.
0.5 T squared.
No. How can you get rid of that fraction? Instead of multiply by half, what can you do?
Multiply by 2
Yeah, so then I get 2D, then divide by,
T squared.
there you go. So 2D over T squared equals acceleration. We're going to use this a lot because this is the easiest way to calculate acceleration. Because acceleration is tough to measure quantitatively, okay? But it's easy to measure distance, it's easy to measure time, and we're always going to start with this thing at rest. So this is the most common way we will use to measure acceleration, okay? So somebody take your calculator, take 2 times a half a meter, otherwise known as 1, and then divide that by 3.50 seconds squared. So what'd you get? Somebody take your calculator. Nathan, what'd you get?
0.08.
0.08?
Yeah.
Exactly?
0.82.
Meters per second squared. Okay? Now, notice that if you look at what happens when you drop something, okay, that acceleration is 9.8 meters per second squared. This is much, much less than that, okay? It's a very slow acceleration. But at this point, we can do a whole bunch of things with it. So now, we could look at it and go, okay, hey, we could draw a velocity time graph. Our velocity time graph is going to be a linear function, and now we know the slope of that line. Ah, okay, cool. That's the slope of that line, 0.082 meters per second squared. Now, could I figure out how fast it's going at the end of 3.5 seconds? Could I find the final velocity? Nathan, you shake your head yes. Why? What could I do?
Good question.
You're the one that shook your head yes.
I don't know, I just assumed that you could. So, you can...
Oh, okay, I asked the question, therefore the answer is yes. Okay,
Yes, of
can we
course.
find the cure for cancer? Yes, Mr. Rokamp, we'll get right on that.
Eventually. Okay, so... You could use the V equals V naught plus AT.
Oh, I like that. V equals V naught plus AT. Again, what's my initial velocity? 0. Goes away. Now, at the end of 1 second, how fast were you going? Do not make this difficult. What'd you say? What'd you say, Angel?
0.082.
Fantastic. That's what that means. That's what the acceleration is. This is for every second that goes by, my velocity changes 0.082. So at the end of 1 second, you are going 0.082 meters per second. So if this thing traveled exactly for just 1 second, you would be traveling 0.082 meters per second. Okay, beautiful answer, right? That's what that number means. But we didn't go for 1 second. We went for 3.5 seconds, right? But it's the same idea. So we can go V equals V naught, which is 0 meters per second. We don't have to solve for anything. We have an acceleration of 0.082 meters per second squared and a time of 3.5 seconds. So Nathan, take 0.082 times 3.5.
You get 0.287.
0.2, call it 0.28 meters per second. Okay? There you go. So once you get numbers, you can do a lot with it. you can draw a position time graph and go, okay, I know my position time graph is going to look something like this because it's a quadratic function. So at the end of 1 second, if you were to draw that tangent line, that would have a slope of 0.082 meters per second because that's how fast it's going at the 1 second. At 3.5 seconds, if you were to draw that tangent line, that would have a slope of 0.28 meters per second. Okay? See how it all fits together. All right. Now, here's the last equation. And it's v squared equals v naught squared plus 2ad. Now, this is the only equation that has a name. Okay? This started 7-8 years ago, and a kid by the name of Nettie, who sat right there where Angel does, for whatever reason, he goes, Burkamp, there's like 4 equations. He wanted to keep them straight. He goes, can we name them? And I said, okay, pick one. He goes, let's call this one that equation right there. He goes, let's call it that equation. I said, okay, cool. We'll call it that equation. So when we talk about that equation, this is the one that we're talking about, okay? That equation. V squared equals E naught squared plus 2ad. That is known as that equation. So when we talk about this equations in this class, we go, oh, Burkamp, let's use that equation. This is the one that we're talking about. Okay? Now, if you look at the other ones, V equals V naught plus AT. Distance equals 1/2 V plus V naught time. D equals 1/2 AT squared plus V naught time. What's unique about that equation? What's missing from that equation that's in the other ones? Time. So if you ever get a problem, and you're going to, that doesn't involve time, use that equation. Okay? Literally. That equation exists in situations where you don't have time. So if you get problems, and you're going to, that don't have time, it's like, oh my God, I've got to find time. No, that's why we have that equation. Don't flip out. Okay? That's why you have that equation. Now, about the first week of May, when we're studying energy, you will see where that equation comes from. Okay? It comes from the conservation of potential and kinetic energy. Potential energy is mass times gravity times your height. Kinetic energy is 1/2 mass times velocity squared. Don't worry about that for now. Eventually, you will see where we get that equation. Okay? And it comes from the conservation of energy. For now, just accept it. So there's a couple of things that are unique about that equation. That's why it's called that equation. It's the only one that doesn't involve time. It's also the only one that has velocities that are squared. Okay? That's the other thing that's important. This is the only one that has velocities that are squared. So here's how you could use that equation. So let's say that you've got yonder carrot car, okay? And let's make it simple, and let's say that it starts at rest, okay? So this is how this would play out. So here's the car, and you know that it's going to speed up over a distance of 10 meters, okay, because that's something that we can easily measure, okay? We can go out into the parking lot. We're going to use Devin's car. Devin, you're going to start at 0, and then we're going to have him speed up, and then we're going to have him go for 10 meters, okay, which is about kind of the width of this ring. That's about 10 meters, okay? And then I'm going to say, Devin, at the end of that time, I want you to look down and tell me how fast you're going. Okay, he does that. Devin looks down. He's got the cool speedometer that measures in meters per second. And he looks down, and he's going, I don't know, 16 meters per second, just to pick a number, okay? And we want to figure out what's his acceleration, okay? So this is pretty simple. Literally, we would go out in the parking lot. We'd make a mark. Here, 10 meters later, we'd put another mark, okay? And then Devin's going to start his car at rest. He's going to punch the accelerator. Devin, when you cross that mark, tell me how fast you're going. He's going to look down, okay? It's a pretty simple experiment. We don't have to have anything high-tech. He just has to be able to look at his speedometer when we cross a point. Okay, it's simple, right? Now, again, here's what I'm going to do. V squared equals V naught squared plus 2AD. If you like the VDAT, notice that this has no mention of time. So as soon, if you do the VDAT chart and you see nothing that involves time, right away think that equation. Okay? Literally, think that equation. So my acceleration is what I don't know. I know my distance is 10 meters. V naught is 0. Final velocity said was 16 meters per second. So I've got this equation. So what I need to do is solve this for acceleration. So, Peyton, how can I get acceleration by itself?
Divide by.
Nope. Start with subtraction.
Yeah, subtract the v naught squared.
So I'm going to have v squared minus v naught squared. Then
Divide by 2.
divide by 2d. There's going to be my acceleration. Okay? I beg of you, I beg of you, I beg of you, solve these equations first and then put in the numbers. It's going to make your life so much simpler. And to realize some of you are like, oh, Mr. Rickett, we've never done that before. Okay, you've never taken physics before either. You've never done upper level science. This is how upper level science is done. Okay? You solve the equations first. Then you put in the numbers. Okay, so in this case, I'm going to have my final velocity. Now, before we do any math at all, is my acceleration going to be a positive or negative number? Is my acceleration going to be a positive or negative number?
Positive,
Why?
because you're speeding up.
That's half the answer. I'm speeding up, but what's the sign of my velocity?
Positive.
So I'm speeding up and I have positive velocity. Therefore, I have to have positive acceleration. If that had ended up being negative 10 meters per second, I would have to have a negative acceleration. And again, I cannot emphasize this enough. Every problem you are going to have, starting today, you're going to have your first real physics assignment today. That's the name of the title, the first real physics assignment. Every problem you're going to have, I only have two tricks. I have two tricks, and two tricks only. When I wrote that problem, am I going to make this thing speed up, or am I going to make it slow down? That's it. There's the only two things I have. Every problem you're going to have is only going to do one of two things. I'm either going to make it speed up, or I'm going to make it slow down. That's it. That's it. Nothing else. And as soon as you read a problem, you go, oh, a robot is speeding up. Right away, you think, wow, acceleration and velocity have to have the same sign. As soon as I tell you, oh, the plane is landing and it's slowing down, right away you think velocity and acceleration have opposite signs. Okay, that's it. Okay, those are the only two tricks that I can do. Literally, something speeding up, make them have the same sign. Something slowing down, make your velocity and acceleration have opposite signs. There is no exceptions to this rule whatsoever. Zero, zip, none. Okay? Can't happen. All right, now, somebody do the math. Somebody take square 16 and then divide that by 20. What'd you get?
12.8.
12.8? Which is actually, that's an amazing acceleration for a car. Okay, this would have to be like a top-end, like, race car to get that kind of acceleration. Okay, but I just made up the numbers. Realistically, when you get accelerations on cars, they're typically around 4 to 8 meters per second squared. Okay, so if you ever get an acceleration of a car and you get like 30 or 40 meters per second squared, you have done something horribly wrong. Okay, typically accelerations of cars are around that 4 to 8 range. Okay, so I'm done. So stop that. Let me hand out your first real. Now, on assignments like this, which is going to be the vast majority of the assignments that you're going to have, I want them done in a very specific manner. So on the back side over here, I've given you an example of how I want this done. Now, here is why I want you to do these this way. Every time I give you guys an assignment, I've got like 16 papers to grade. The reason I have you do this is because it's an efficient way for me to grade your papers. That way, I don't have to guess where, Alexis is putting her answers versus where Tyler is putting his answers, and then everybody's like scattered out, and I'm trying to figure out, okay, where are your answers? Well, I'll box them. Well, that doesn't help. So the reason that I want you to do these assignments this way is because that way I can just go straight down one side of the paper, I can see your answers. And then over here, I can see the work that goes with it. That way, I don't have to try and sort through where the answer is and everything else like this. So, if you look on questions 1 through 6 up at the top, those are just multiple choice questions. So here's your paper, okay? And some people take this to extremes. So what you want to do is come over about inch and a half, 3 or 4 centimeters if you're into that. And you're going to draw a line. And some people take a ruler and they draw a very, very, very nice line. Okay? And the only thing that I want in this column to the left are your answers. Okay? And you're going to go 1, 2, 3, 4, 5, 6. Okay? Not a big deal. First ones are multiple choice, those are easy. Okay? Boom, there's your answers. And if you, none of these on these multiple choice questions require any calculations. This is just general knowledge kind of thing. So there's nothing really to put over there. Now, when you get to number 7, okay? When you get to number 7, I say, can an object move with uniform acceleration and constant velocity at the same time? Explain. And I'm going to make this note. 0 meters per second squared is not considered an acceleration. Okay? That's like saying, I have no money in my bank account, but yet I have money. No, you don't. You don't have any money, okay? If you have 0 meters per second squared, that is not an acceleration, okay? So don't get technical and go, well, if it's 0, no, stop, okay? 0 meters per second squared is not an acceleration, okay? 0.1, that's an acceleration. 0, not an acceleration. So when you answer number 7, you can write across this whole thing, and you can go across like that. The nitpicky part comes when you get to number 8. Okay, so here we're going to work number 8, so I can show you exactly how I want number 8 done. I'm going to work number 8. So here's this line, and I'm going to put my answer right there with that. So if you read number 8, a rocket lifts off its launch pad and travels straight up, attaining a speed of 100 meters per second, 10 seconds. Calculate its acceleration. So if you like sketching stuff, physics is your jam. Okay. Literally, if I were doing this, because I just always like to sketch, I'm going to go, okay, here's my rocket, okay? Now, and again, you don't have to do this, but if you want to do the VDAT thing, okay, and you read this problem, you go, my God, I have no idea what's going on. At least identify the variables. So what do you think the initial velocity of the rocket is going to be? 0. The rocket is sitting here, okay? It's at rest. If the rocket was moving, I would have to give you that velocity. So my initial velocity, 0 meters per second. 100 meters per second. What's that going to be? Final velocity. Okay, my final velocity is 100 meters per second. Distance, not part of the story, okay? I don't talk about distance. I don't give you the distance. I don't ask you to find the distance. Don't worry about it. So then you've got calculate the acceleration. That's what I don't know. I know my time is 10 seconds. Okay? So I've done the VDAT chart. Again, you don't have to do the VDAT chart. I recommend it, not mandatory. Okay? But if you come in tomorrow morning, you go, Mr. Burkamp, I have no idea how to do number 12. And I'm going to ask you, have you set up your VDAT chart? And if you say, no, I'm not being a jerk, but I'm going to tell you, you go set up that chart and you fill in that information and then you get back with me, okay? Because until you figure out what you have, you can't solve the problem. Now I need to choose an equation. Now, y'all only have 4 equations to choose from. Okay? You only have 4 equations at this point in your physics career. You only have 4. What equation are you going to pick? Jack, what would you recommend?
The find acceleration.
Not yet, find the acceleration, knowing initial velocity, final velocity, and time. What would you recommend?
V equals V naught plus AG.
Fantastic. Okay? Good? Okay. Now, here's the story. So I need to solve this for acceleration. Okay? That's what I'm trying to find. Solve the equation first. Okay? So how are you going to get acceleration by itself? Hector, what am I going to do?
You're gonna subtract the V naught,
And then what?
divide by time.
Boom, there's my acceleration. Now, you have to view this from the perspective, of me, a pair of 56-year-old eyes that have seen a lot in this world. You're trying to convey to me how you solved the problem. What did you do? What was your process? Okay? This is not about just the answer. This is about the process. Pay attention to the process. The product, the answer, will take care of itself. Okay? Now that I'm to this point, now I can put in the numbers. Now I can take 100 meters per second minus 0 divided by 10 seconds. And you get 10 meters per second squared. Now, here's what I don't want you to do. Don't come over here and write 10, okay? Because that's a train wreck for any number of reasons. Number one, you only have one significant digit. I gave you 3 significant digits in every value that you have. You have good data, okay? If you just put 10, that only has one significant digit. Also, why am I going to flip out if let's say you even put 10.0. What does that mean?
Could be squirrels.
Yeah, could be squirrels, penguins, velocity, time. I don't know. Okay? This is why you pay attention to the units. Oh, that's meters per second squared. So, again, every time you write an answer, you have 2 decisions to make. How many significant digits are you going to put? What units are you going to put? Okay? And pay attention to that as a problem. Now, then you're going to get to number 9. So here's what I don't want you to do. This will just drive me absolutely crazy. This is the worst thing you can do. Is then put number 9 right below number 8, and then have the work for number 9 down here. Okay? Horrible. Stop. Don't. You want to keep that answer to number 9 right beside the work. So you're going to put number 9 down here. Now what I would like for you to do is to actually leave a space in between these. Because that way I'll know when number 8 stopped and number 9 started. Because you don't want all these blending together. Because love you all to death, I do. But I am not going to spend my evenings trying to sort through random numbers that don't make any sense. Okay? And me trying to guess what you have done. Not going to do it. Okay? Do not view this through a teenager's eyes. View them from a cranky old 56-year-old physics teacher's eyes that I don't want to spend my remaining time trying to sort through mumbo jumbo. Now, what some people, you don't have to do this, but some people actually, they get into shading and they'll like shade in the lines so that there's a break, okay? Some people go hardcore, they'll put like stars, okay, in between. You don't have to do that, okay? If you want to, great, fantastic. You don't have to put stars or shade it. You don't have to do that, okay? You don't have to do. But at a minimum, leave a space in between number 8 and number 9. Now, when you get to question number 11, okay, number 11 has a whole bunch of parts to it. Even within number 11, like for example on number 11a, it says draw a motion diagram with at least 2 velocity vectors and acceleration vectors. So what's happening on number 11? So here's Carson. She's playing softball, and Carson is sliding into second base, okay? So she's moving at 4 meters per second. and she's going to come to a stop when she hits the bag, okay? So when I say draw velocity vectors, here's all what you have to do. Say, here's V1. Just draw a velocity vector. She's going in this direction. Now, one of two things is going to happen when you draw your second velocity vector. Either she's going faster, and you draw the second velocity vector bigger, or she's going slower, and you draw it smaller. Okay? So, Carson, what happens when you slide into second base? Do you speed up or slow down?
Slow down.
You slow down. Okay? So then I'm going to draw V2 a little bit smaller than that. Okay? That's all you have to do. That's it. That's all you have to do for the velocity vectors. You either make them get bigger or you make them get smaller. Those are your only two options. Now, if you're slowing down, which direction is your acceleration vector going to point? In the same direction or the opposite direction? Opposite. So then just come in here and go, oh, I'm going to have some negative acceleration. And I'm going to have negative acceleration because she's slowing down and she has positive velocity. So on 11A, that's all you have to show. Couple of velocity vectors are getting smaller, draw an acceleration vector pointing in the opposite direction. That's all you have to have. Do not make this complicated. Then on B, it says, what's her acceleration? So 11A, boom, here's your line. You've got those vectors over here. Boom, that's all you have to have. Now, when you do 11B, I want the answer to B here and the work over here. When you get to C, it says make a simple velocity time graph. You can draw the velocity time graph on the sheet of paper, or if you really want to get hardcore, you can get a sheet of graph paper and draw it there. But all you have to do on your velocity time graph, this is just a sketch, okay? Just do this. Just, if you want to put it on another sheet of paper, that's fine. You can just put it over here. Then you get to D. How far did she slide? D is going to be a distance, okay? Over here, I'm going to have the work that generates D. Just like that. So when in doubt, space it out, okay? The worst thing that you can do is cram all this together. My blood pressure will go up the minute I see your paper, and as soon as my blood pressure goes up, your grade is likely to go down because there's an inverse relationship between those two. Okay, now let me give you a hint. If you look on number 17 on the back side, yes, there is a back side. It says driver is traveling at 20 kilometers per hour, stops the car in 3 meters. Later, while moving at 40 kilometers per hour, stops at the same acceleration. When you read 17, what do you not have? What variable is missing in question 17? What is not there? Time. So what are you going to use? That equation. So on 17, you're going to use that equation because you don't have time. Okay? Now, you have kilometers per hour. Over here on the front, okay, up here at the top, it says, all calculations must be done in the MKS units of system. What this means is that you cannot leave the kilometers per hour in kilometers per hour. What are you going to have to change it into? Meters per second. So now, let's make sure everybody's cool with this. I'm going to take 20.0 kilometers per 1 hour. How many significant digits are in 20.0? 3. 20.0, 3 significant digits. That's per 1 hour. Remember, in 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. Shortcut, you multiply by 10, you divide by 36. Now, when you do this conversion, okay, somebody do this. Somebody take 20 times 10 and divide that by 36. You get 5 point something, I think.
$5.5.
Okay, 5.5 what?
5.6.
Okay, you get a whole bunch of repeating 5s. This has 3 digits in it. When you do that conversion, do not round that converted value into meters per second. At a minimum, you keep it as 3. Okay, at a minimum, you keep it as 3. Do not round that to 6. Do not round that to 5.6. you keep at least 3 digits when you make a conversion from kilometers per hour into meters per second, okay? Because every one I'm going to give you has 3 significant digits. So do not round that too much. Okay. All right. So you can do this on a complete, even the multiple choice. Those 1 through 6, do not circle them and expect me to grade this. I'm not, okay? When I give you a piece of paper, an assignment like this, where if I want you to answer assignments on a piece of paper, I will give you lines to write them, okay? There are no lines here, okay? You answer, you treat this like a page out of a textbook. You can write on it, okay? Not a big deal. But how you answer this, you answer nothing on here. I will not look at this page at all when I go to grade your paper, right? Will not even look at it. Okay, I'm done. Good luck on your first real physics assignment.